Most Americans think the right to vote is among the most important tools that they have to participate in our democracy. You do agree, don't you, Judge Roberts, that the right to vote is a fundamental constitutional right? Judge Roberts says it is preservative. I think of all other rights. Without access to the ballot box, people are not in the position to protect any other rights that are important to them. And so I think
Anybody recognize what we were listening to? Yep, that's right, Jesse. SCOTUS confirmation hearings. I think it was Senator Leahy, a Democrat from Illinois, was asking Judge Barrett questions for the last few minutes. Yeah, important stuff, interesting stuff. It's always, I find it fun or interesting to see how things happen in Washington, D.C. Sometimes it's hard to know if you're seeing the whole truth or just part of the truth. But if you pay attention, at least you're getting some of the truth. And one of the things we learn in college, we take all these courses, all these GE courses you take, you think they're kind of a pain because they don't have to do with your major. Well, the GE courses are where you pick up tools that allow you to evaluate what you're seeing in the news and evaluate what you see in the newspaper. History, philosophy, statistics, all kinds of stuff. Ethnic studies. We use our college degree every day and in life, and a lot of times we don't recognize when we're using it. A lot of people say getting a college degree enriches your life. You have a richer experience in life because you have a college degree, because it sets you up to understand more things and be able to learn more things as you live. And I really believe that. So, yeah. I'm sitting here trying to prep my iPad so I can start displaying notes. Ooh, we're talking the 14th today. Anybody have anything that's on their mind they want to talk about? Any things that are happening that you want folks to know about, or any questions you have for me about the course? I'll try to capture them if you ask those questions. Everybody good this morning? Everybody okay? Hanging in there? Thumbs up,
Doing
thumbs
good
down.
enough.
Good enough. That's all it takes. Sometimes it's better if it can be really good sometimes, and then good enough will get us through. Yeah, good. I'm glad I'm seeing some thumbs up. Me, I'm almost a thumbs up, I think. I'm sitting at this desk too much. I'm doing too much work. But that's all right. It's for good cause. All right. Any questions before we launch into more calculus? I can think of an announcement or two I want to make, and I'll do that in a second. Yeah, Jet, I see your comment. That's one of the things I want to talk about. Anybody else have a question or a comment?
Oh, when you said to email you, do you want us to do it through Gmail or do you want us to do it through Canvas?
I prefer getting it directly. Don't go through Canvas because sometimes I lose it or it doesn't get to me. So just email me directly. I don't care what email account you email me from. I just need to be able to recognize you. And usually when you sign your name, that's good enough. My browser recognizes people who send me email from within CI. But yeah, thanks
All
for
right.
asking. So I'm going to share my iPad. Let's see if it works today. Awesome. Okay, I'm recording. I think everything looks good. Let me arrange windows I have here. Opening the chat. Okay. So the date is 14 October. This is Calc 1. So let me say something about grade reports. If you've taken the Learning Target quiz before last Friday, I still have a backlog of Learning Target quizzes I haven't graded yet and did not make it into the report. But if you've, before last Friday, if you've taken a Learning Target quiz, then you should have received a grade report by email. Yesterday morning. If you did not receive a grade report, it means that you have not taken a Learning Target quiz yet, and you're way behind, okay? And you need to catch up. There are quite a few people that fall into that category. Now, many of you that didn't receive a grade report, you probably took a Learning Target quiz in the last week or week and a half, and I just haven't gotten to it yet. But if you know if you've taken Learning Target quizzes yet or not, if you haven't taken them, I'm here telling you, you're behind. You need to pick up your game. I'm concerned about you. So I will just leave it there. We're all adults. You know what that means. You have agency to fix that. Time is lost. You can't make up the time, but you can fix the situation of not making progress. There are probably errors in grade reports. And one of the reasons I send them to you, and I wrote this in the short email that you received with your grade report attached, is I want you to look at the grade report. And if there are errors, let me know, because that feedback I get from you will let me go back and find the errors. I'll go back and look. And if I disagree with you, if I feel like the report was correct after I go back and look, we'll have a conversation and we'll figure out which one of us is incorrect. I recognize you as being the authority on what you have done and where you've got, where you've demonstrated mastery and where you haven't quite demonstrated mastery yet and where you haven't tried yet. You are the authority on that. I'm trying to do that for 60 people this semester, and so I can't keep everything at the front of my mind. So these grade reports are a way for us to have a conversation to make sure we're on the same page, right? So don't feel like intimidated by me having a conversation with you. It's not going to be accusatory. It's going to be, hey, let's figure out where I, Dr. Miller, made the mistakes. In the way I do this, there's 15 places that I could introduce a mistake because I did something stupid, right? And I am really stupid about lots of things. I can't type. So why I'm using a computer program that I wrote to do this stuff is beyond me, but I am. So there's lots of places where error can happen. You can help me catch that. So don't be frustrated. Don't be intimidated. We'll talk about these things and we'll figure the errors out. They'll get figured out pretty quickly. So I need, you to help me fix. Okay, so that's grade reports. Learning target quizzes. I'm going to add another L4 because at least one person has told me that they want another L4. And Summer, I see that you're asking about D2 and D3. Yeah, we're definitely at a place where people can be taking those, and I will add those. And I'll add the rest of the Ds. Okay. and I'll work on that during office hours today at noon. So I'll get on Zoom. So if people want to come and ask me questions, I'll be there. But one of the tasks I'll be doing is updating these learning target quizzes. Okay. So if there's ever a time when you want to take a learning target quiz and you can't find one that you can take, email me. And if it means I got to write one, I'll write one. If it means I just have to adjust and post one that I have and it's just not accessible to you yet, I can do that too. So don't hesitate. Okay. Right. So that's the learning target quizzes. Any other business people want to talk about? We're at the midterm of the semester, so I'm going to send you. It's my practice. I like to do this. I like to send out a midterm student survey where I ask you how things are going in the course. It's totally anonymous, and it's just a way for you to give me some feedback about what's going well, what's going not so well. And I do this even when we're not in a pandemic, but this would give you a chance to give me some feedback about what pandemic adjustments are working and what pandemic adjustments aren't working. So keep your eyes out for that. I appreciate everybody responding. You don't have to answer every question if you don't want to. If some of them make you feel uncomfortable, don't answer them. But I assure you, they're all anonymous. I don't care who. I do not track who sends what back. And then what I will do is that if enough people respond, I will share the results of the survey with everybody in summary form. Because you all deserve to know how your classmates are feeling too. Anything else? All right, Lupe, is anything you want to tell the group?
Just a reminder that you guys have today your drop-in hour from 7:30 to 8:30. I am there till 9, so even after, stay after. That's about it. Just a reminder, you guys should come in. I got permission from Dr. Miller about reviewing. If you guys need help reviewing your previous learning target quizzes, maybe understanding what he wrote down or stuff like that, you guys can come in.
Yeah, hey, that's a great point, Lupe. So his drop-in hours are today. The Canvas landing page down, if you scroll down toward the bottom, it'll list the times when Lupe's working. It also lists his special drop-in hours where you get priority. So you jump the line basically. But go work with him. I mean, he is in class with us every day. So he knows what we're talking about and he knows how I'm talking about things. One of the frustrations students often have when they go to the LRC or the STEM Center to talk to a tutor is that the tutor starts explaining something in a way that's totally different from the way their instructor talks about it. And the tutor doesn't know the context of questions and stuff. So Lupe is not going to have that problem, right? Lupe knows the way we've been talking about things. He has access to our Canvas course. He can pull up the notes that I post from class. So he's like the perfect peer tutor for you in this class. And also, I'll just amplify what Lupe said. If you got a learning target quiz and you want to figure out what I meant by something, or why you got something wrong, it's not clear from my comment, then go to Lupe. You can absolutely positively talk to Lupe about it. I have no problem with that. And you're welcome to talk with other students in class about a quiz you took, as long as they took the quiz too. You know, it doesn't even need to be the same version of a learning target quiz. As long as they've demonstrated mastery in that area and they're not going to take those quizzes anymore, go ahead and talk about it. To share your work on a quiz that somebody else hasn't mastered yet, that's a violation of academic integrity. And so I ask you not to do that. But as long as somebody else has passed the same target as you, yeah, go ahead and talk about those quizzes. And you can always talk about it with Lupe. The one hitch there is if you're there meeting with Lupe and somebody else starts talking about a learning target that quiz and you haven't taken that one yet or haven't demonstrated mastery on that one yet, I ask you to somehow plug your ears and do the la 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 thing, or however you can manage that. I mean, I'll trust you to manage it, but I just wanted to put that out there. Anybody have any questions or concerns about that? And I can't emphasize enough the importance of talking about mathematics with your classmates. Talking about this stuff is an important aspect of learning and studying. It gets it into a different part of your brain, and it gets it deeper into your brain. Writing about mathematics is one thing, writing up on scratch paper solutions to problems, that's one thing. Talking about it with somebody else, being quizzed by somebody else, quizzing somebody else, that's another thing. That brings you to the next level, and that's really important. And it's especially hard during the pandemic because we're not running into each other on campus. But maybe Zoom makes it easier. Maybe Zoom is making it easier during the pandemic for you to meet with other classmates because you just have to schedule something and nobody's got to drive anywhere. You just get online as long as you've got internet access. And then I'll just remind you that Lupe's said that the STEM Center can set you up with a Zoom session that can last as long as you want it to last. You're not limited to like the 40 minutes that Zoom imposes on CI students when they do it themselves. Hey, that's great. Yeah, use the chat. Jet Summer. Maybe you didn't mean to do that publicly, but yeah, use the chat to connect, right? And then when people share information with you, just use it responsibly. Okay. All right, let's talk about math. Anybody have any questions about what we've talked about so far up to now? No questions? Okay, so let's do a 3, 2, 1, go exercise. You ready for this? Last time we talked about a bunch of stuff. So I want you to think about class on Monday and think about some of the new things that we talked about. Some new vocabulary, some new ideas, some new types of theorems we threw out there. And I want you to type one new thing we talked about last time into the chat. And then when I do 3, 2, 1, go, you'll hit the enter on go, okay? So I'm going to give you a few seconds to type something in the chat that we learned on Monday. And I want everybody to do it. Everybody who is here, I want you to type in something. Okay. Yeah. So how many people do we have? We got 26 people in here. That means there's 24, not, so if we, dropping me and Lupe. So I want to see 24 things come through the chat, right? There's gonna be lots of repetitions. That's great. But 24 things in the chat, and then watch what comes through the chat. Okay. Ready? 3, 2, 1, go. All right, good. I like it. Athalia asks, what if we already knew this vocab? I wasn't asking if you knew it. I was asking what we talked about. So it's good if you knew it. I was asking about what we talked about. All right, so let me ask this question. So not everybody responded. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 people responded. So we were missing 6, and you know who you are. To you, all right? Let's do better. Here's another question that has one answer, okay? There's one answer we're looking for. What was the most important theorem? What was the most important rule we talked about last time? Okay, think about that, and then we'll do the 3, 2, 1, go. What was and I said it multiple times, what was the most important result we talked about in class on Monday? Okay, I'm about to start the countdown. Type something in. 5, 4, 3, 2, 1, go. Yeah, good. So Summer and Anthony, you both put the same thing in there, and that was something we brought up to prove the power rule. So I will give everybody credit for getting it right. Summer and Anthony, you are just a near miss. Okay, so that still counts in my book. Yeah, the power rule was the most important thing we talked about last time, and that's just the power rule says. And here I'm on my iPad. If you take the derivative of a variable to the nth power, okay, so the variable is in the base, and n is just a constant in the exponent. That's n times x to the n minus 1. Okay. Now, I'm gonna write this little red thing in here. N can be any real constant except n equals 0. Because the way I want you to think is that if n equals 0, then this is a constant. And then automatically you know that the derivative of a constant is 0. So I don't want you to be using the power rule when you have a constant. Okay? I want you to think about that as something separate. Well, Dr. Miller, there's an n right here. Yeah, okay, there's a consistency, but the proof doesn't work. Well, maybe the proof does work. That's still not how I want you to think about it. Okay. Right or wrong, that's not how I want you to think about it. Okay, so product rule is something we talked about. That was in the chat, and the last thing was something else that came up. Binomial theorem. Okay, that's not super important. Okay, that was just kind of a bonus cultural thing. Leibniz notation. Prime notation, though we didn't introduce that last time. We've talked about that a while ago. Derivative operator. Right, and so that's thinking of the derivative as a verb, right? Like taking a derivative. What else showed up? Okay, those are the things that showed up in the first list. Anybody else want to throw anything in the chat that hasn't been put there yet, but that we talked about last time? You can vocalize it too, I suppose. Nobody? I can think of 3 other. Okay, Pascal's triangle, right? So that kind of goes along with the binomial theorem, in that it's not hugely important to understanding calculus, but it's important when we're talking about the proof of that power rule. The bar thingy. What's the bar thingy? Oh, the vertical bar thingy, right? Yeah. So if I said something like this, that's the same thing as f prime of x naught. Yep. So that vertical notation, very good. Vertical bar notation. The notation break. Yeah. So that was. Oh, go ahead.
Oh, sorry. You said that all of these were second level principles.
Yeah, second level principles. What did I mean by that?
I'm reading it right now. So they're the proof of they're the proof of these formulas, and then you said they're all from the first principles, and then you use the definition of the derivative.
Yeah. So this idea of there being a second level means that they're a theorem that uses the first principle, that is the definition,
Oh yeah.
in its proof.
Mhm. So we were talking about, what was it? The tangent. The tangent.
Yep.
formula?
So the most important thing that I want people to get out of that conversation is that the idea that the first principle is the definition. So if anybody asks you to do something from first principles, it means use the definition. So I might say that on a learning target quiz. Use first principles to calculate the slope of the tangent line or something. So important phrase. It's kind of nerdy. It makes you sound smart when you use a phrase like that. I just wanted to make you aware of it. Okay, come on. There's 3 more rules I want you to mention. Nobody's mentioned these other 3 rules. Can somebody throw into chat one of the rules that people haven't mentioned? Very good, Robert. Quotient rule. 2 more. Or 3, depending on how you count. Haven't done chain rule yet, Selena. Maybe later today. Probably on Monday. Sum and difference. Jet gets a twofer. The sum and difference rule. 1 more. 3-word rule. Very good, Athalia. The constant. Yep. Yep. Okay. And I'm going to add in this from the last page, product rule. This was the big theorem last time. Well, it was the big theorem, the one that took up the most space. Okay. And it gives us techniques for calculating the derivative of functions, right? So what I'm going to do, what do I want to say about this? What do I want to say about this? Well, let's do this. Let's just state them. You got 2 functions that are differentiable at some point. You've got a number k as a constant. Then what we proved is that all kinds of algebraic combinations of these 2 functions are also differentiable. So if you take the derivative of k times f of x, that's k times the derivative of f of x, right? You can pull that constant outside that derivative operator. If you got the sum of 2 functions, the derivative of that is the sum of the derivatives. So this is like a distributive property of the process of differentiation. And then that also works if you're taking the difference. So that's why we call that the sum difference rule. And then the 2 big ones, well, they're all big, but the 2 that I've written down so far really mirror laws of limits that we saw, limit laws that we've seen. And so the product rule is the first one that has a more complex pattern. And so this is a formula you have to memorize. The derivative of the product of 2 functions, the derivative of f times g, is the derivative of f times g plus f times the derivative of g. And you could also write this, it's kind of easier in prime notation. There's less stuff to write down, fewer symbols. Okay, you can write it that way. And then the quotient rule, the derivative of f divided by g, it's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So using prime notation, it's a little more compact. It looks like that. And I made a special effort to draw your attention to that minus sign there, okay? Because the plus sign here makes remembering this formula forgiving. You don't have to worry, like, which is the term that has the derivative first? The minus sign here makes this quotient rule less forgiving, okay? And you need to memorize it in this order. Derivative of top times the bottom minus top times the derivative of the bottom. Okay. Big important rules. You got to know them. And I'm going to show you some screencasts that explain the proofs. I hoped I would have done that by today. Hasn't happened. So let's just do a couple examples of practicing with the product rule and these differentiation rules. So let's take a function. I'm just going to take a polynomial. Let's say it's a 4th degree polynomial. So x to the 4th. Yeah. Okay, that's an important popular polynomial. Let's find the derivative. All right. So f prime of x is the derivative of this algebraic expression, what we call a polynomial. And so we're going to use the sum rule. And it tells us that the derivative of a sum is the sum of the derivatives. Oops. So I've got to distribute this derivative sign down all of these. Okay. So that's using that theorem once. Now we look at the last term, that derivative of 1, that's a constant. So the derivative of a constant is 0. So that's done. And then each of these terms, each of those terms is a monomial. So I can just use the power rule. So the derivative of x to the 4th, I take the exponent down, becomes a coefficient. And then I subtract 1 from my exponent. And then I do the same for each of the others. And now let's just simplify that. And there we go. There's the derivative. So that's one example of how we use the derivative formulas to calculate the derivative of this polynomial. So a fact, we can now differentiate any polynomial using those rules. So you can differentiate any member of that family of elementary functions that we call polynomials. Here's fact number 2. If p of x is a polynomial of degree n, then p prime of x is also a polynomial, right? We saw that here. This is a polynomial. Differentiate, we get that polynomial. But the derivative has a degree of n minus 1. So it's got a lower degree. So that's always going to happen. So that's kind of cool. It's a consequence, of course, of the power rule. Any questions before I move on? Oh, so Alexia, you asked, how do we know to start with some difference is because they are being added? And Lupe says, yeah, that's correct. So here.
I had one more question also.
Yeah, sure.
So how do we know that that is the answer? Like to stop there?
So good question. So how do you know that that's the answer?
Mm-hmm.
All right. I'm going to give you two answers.
Okay.
Okay. So with the first answer, I'm going to be a jerk, and the second answer, I'm going to be a little bit more constructive, right?
Okay.
So the first answer, and this isn't the way that I would really. It's kind of not a serious answer because your question is a serious question, and I understand it. So here's the jerky answer. So how do I know when I'm calculating this? How do I know to stop there? So the jerky answer is there's nothing left to do.
Okay. Yeah.
Right? Now somebody could rightfully say, well, shouldn't I see if I can factor that? And I could concede, yes, that would be a reasonable thing to ask. But if you're just being asked to find the derivative, this is an answer. This is a legit answer. Okay. Why do I know there's nothing left to do? Well, the whole objective was to calculate a derivative. And so here I go. Here's my notation for the operation of calculating the derivative. So I recognize I should use the sum rule. And so I do that. I distribute across the sum rule. So now I've got 5 derivatives I'm going to take. And then I take them. So that's done. So somebody could say, well, Miller, shouldn't I just stop right here? I'm all done. No, you've got a little bit more work you have to do here. But once that work is done, there's the function. So in a way, that process of exhausting the derivative, doing that differentiation is done. And so you're done with the problem. Is that kind of helpful, Alexia?
Yeah, I understand, like, I mean, I know in this one, like, you could see that there's nothing left to do, but
Uh-huh.
I know that probably in other problems, it's going to be harder to tell.
Yeah, and I'll try to give you a variety of problems today, and maybe
Yeah.
that'll speak to some of that.
Thank you.
Yeah. So what are some so what are some other things that after you calculate a derivative that you might have ghosts in your mind saying you should do, right? Well, factoring, that's one thing you could always ask yourself if you could do. Simplifying, that's something that you could, a ghost could be saying, hey, you maybe should do this next. If if you're dividing by a radical, some people say that's bad. I think it's fine. So there's a bunch of legitimate things that that inner lizard brain could be telling you, or that inner critic could be saying, oh, well, you should do this next. But I'm just trying to say mathematicians are lazy. Just remember, mathematicians are lazy. They don't want to do more than they have to do. And so if a mathematician tells you to find a derivative, she means find that derivative. And when you get that derivative, listen to her and don't do anything else. She doesn't want you to do anything else because she's lazy too. Okay. If she says,
Okay, thank you. Yeah.
yeah. If she says find where the derivative vanishes, well, then you're going to have to factor. Okay. Yeah. So in mathematics, following the directions, on the one hand, it's a pain in the ass, but it's important because it also tells you when you're done. I mean, it's a legit question, Alexia. I thank you for asking it. Because there's a lot of anxiety a lot of people feel when they're working a problem and they want to figure out when they're done, and so that's I'll just leave it there.
Thank
Brandon,
you.
yeah. Brandon asked, couldn't you keep doing derivatives until you get the derivative of 0? In theory, Brandon, you could, because of these facts here, right? Or especially the fact 2, because when you take a polynomial and you take its derivative, the derivative keeps getting reduced until at the end, when the degree is 0, you've got a constant, and then the next derivative, you've got a derivative that's identically 0. So from a theoretical perspective, yeah, you can keep doing that with a polynomial and you will get 0. There's lots of other functions where that doesn't happen. We'll talk about that later. But in this problem, derivative once, don't do anything more. Is that what you're asking about, Brandon? I guess we'll never know. Okay, let's move on. Let's do another problem. So let's do a practice with a quotient rule problem. Okay. And let's differentiate x minus 1 over x squared minus 4. Okay, let's find q prime of x. All right, so I've got a polynomial upstairs, a polynomial downstairs. So I want to look at this rational function as being the quotient of two polynomials. And that's how I see this as being a quotient rule. Whenever you see a line like this, you're dividing one thing into another and you're asked to take a derivative. Quotient rule, right? That screams quotient rule. All right. So by the quotient rule, you always know you end up with a denominator that's the square of the function, the square of the denominator you're given. And then we have the derivative of the top times the bottom minus the top times the derivative of the bottom. And sometimes, just in case there's a question about what you're differentiating, it might be good to put another pair of parentheses around that derivative there. All right, and now we're ready to compute. So I'm going to rewrite the denominator since I'm already done with that. So the derivative of the first term, I'm going to use the sum rule here. And rewriting other things, I'm going to use the sum rule down here. Okay, everybody follow me? Everybody good? Robert's good? Okay. So I have this function, and now I'm using the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Then I use the sum rule to calculate the derivatives I have upstairs. And so I get 1 minus 0. And then here, the power rule gives the derivative of x squared is 2x. And this thing here is the number 1. Don't have to worry about that. So my simplification, I get x squared minus 4 minus x minus 1 times 2x. All right. So now I could ask the Alexia question and say, am I done yet? And on the one hand, this is the derivative. Okay, we have calculated the derivative. But on the other hand, if you're anal retentive, you say, well, isn't there some cleaning up I can do here? Isn't there some organization I can do? It seems like it's a little messy. And the answer to that would be yes. And so it's not a bad idea to multiply out and then simplify. Because in the end, you never know what kind of cancellations you might have. So it looks like we get minus x squared minus 2x minus 4, or x squared minus 4 squared. Does the numerator simplify into anything? No. I mean, I could pull a minus sign out, right? I could write this as minus. Sorry, it's so low. I could write it that way. And arguably, this is a nicer representation of the function than this, because now this is ready to do some factoring and stuff. Okay, so although technically you could say that you're done here, it would be a good practice as a math student to simplify your answer. Okay. So I'm going to move on here in a second. We're at 8:45. Do you want me to do a couple more examples before we break, or do you want me to? Do you want me to do a couple more examples and then take a break, or do you want to take a break now? Why don't we take a break? And what I'll do is that after we get back from the break, I'll give you some more examples that aren't super involved of how we use these rules, but they give you they have a different flavor to them. And then we will talk about what does a derivative mean. We'll remind ourselves about what the derivative means and how we think about the derivative as a rate of change. Okay, so let's take a 5-minute break. I will set my timer. And when we get back, we'll work some more examples. And as always, if you've got questions, we can answer those too. Okay, so 5 minutes.
America's Republic Trust, and it shows the dark money connections between Senator Whitehouse and Planned Parenthood and Arabella Advisors and all of these different organizations with money flowing back and forth, all the dark money. And in fact, I would note one of those dark money organizations on the left that we talked about yesterday that is the Demand Justice Organization. I would point out the Demand Justice Organization has decided to be directly involved in these proceedings because this is a left-wing dark money organization that has posters that are right outside of this building that have pictures. Senator Lee, you're on the poster. Chairman Graham, you're on the poster. And the posters say, Supreme Super Spreaders, politics first, health and safety last. You know what? The First Amendment's a great thing. If they want to put your pictures up, it's actually a pretty good picture of Senator Lee. It's not as good a picture. Chairman Graham needs to work on getting a better picture to that. It's not their fault. The Democratic dark money efforts dwarf the Republican dark money efforts, which is why, without a twinge of hypocrisy, Democratic members make this charge repeatedly. And in fact, I will point to one specific example, which is a Judge John J. Jack McConnell, who is a judge in the state of Rhode Island. Now, who is Judge McConnell? Well, he used to be the treasurer of the Rhode Island Democratic Party and the director of the Rhode Island branch of Planned Parenthood. Well, how did Mr. McConnell become a judge? Well, according to CQ roll call, he contributed about $500,000 to Democratic political committees before becoming a judge. This, by the way, is more than any other judge nominated by Obama or Trump. So Judge McConnell stands at the top, $500,000. He donated $12,600 to Senator Whitehouse. He hosted a fundraiser for Senator Whitehouse at his home in Providence in 2006. Judge McConnell's wife gave another $250,000 to candidates and causes, so that's $750,000. And now Judge McConnell is a judge after Senator Whitehouse vigorously led the fight to get him appointed a judge. He sits on the Committee on Code of Conduct of the U.S. Judicial Conference. And what has he done on the Committee on Code of Conduct? He has helped lead the charge to issue a new rule to try to ban judges from being members of the Federalist Society. And to the shock of no one looking at the Red Yarn connections, after Judge McConnell and the committee put out this assault on the Federalist Society to prohibit judges from being members, Senator Whitehouse and 6 other Democratic senators loudly cheered that effort in writing. Now, fortunately, that effort was roundly denounced. Over 200 federal judges signed a letter opposing this. Federalist Society takes no positions, doesn't lobby, doesn't file amicus briefs, doesn't take public policy positions. Most of its events are debates where people on the left are featured prominently. Every single U.S. Supreme Court justice, all of them, have spoken at least one Federalist Society event. And thankfully, the assault on the Federalist Society was withdrawn in the face of over 200 federal judges, and I would note 29 senators roundly criticizing the attempt. Let's turn to the fourth issue. Many Democratic members of this committee seem to be treating this hearing as a policy hearing on what's good healthcare policy, what's good gun policy, what's good voting rights policy. Judge Barrett, in your view, is it the responsibility of a federal judge to implement policy positions that they might happen to agree with?
That's your job, not a judge's.
That I very much agree with. It's easy for someone watching these proceedings to assume both sides want the same thing, just on opposite partisan lines. It's easy for someone watching to assume, well, the Democrats, they want Democrat judges to implement their policy, and the Republicans, they want Republican judges to implement their policy.
All right. Time is up.
Easy as that is to assume,
I apologize. I decided that for the break, I'd turn National Public Radio back on and turn the confirmation hearings back on like I was before class. And then I heard Ted Cruz's voice, and I felt bad for everybody who had to listen to it. So I think regardless of your politics, everybody can agree that Ted Cruz is kind of annoying. Anyway, civic duty, know what's happening in DC. But we're back in our own little ivory tower bubble talking about calculus. And I'm trying, okay, there, I've got the iPad shared again. Over the break, anybody come up with any questions that are on their mind? Ready for some more examples? All right. Robert and Alexia are speaking for the group, saying yes. So here, consider, I'm going to write this down. Notice no numbers. I'm going to use these symbols, A, B, C, are real numbers. So they're going to stand for real numbers. Okay, so they're generic coefficients. So what I've just written down is every single possible polynomial of degree 2. If you think of a polynomial of degree 2, I can turn this into that polynomial of degree 2 by choosing the appropriate values of A, B, and C. Right? So this is an abstract representation of all polynomials of degree 2. Let's calculate P prime of X. and observe the form it takes. Okay. So p prime of x, right? That's the derivative of my function, ax squared plus bx plus c. So something we haven't really talked about in this class are the mathematics order of operations. So when we talk about order of operations, the word operations refers to mathematical operations. And those include like sum and difference. And then we have like multiplication. And we have division. But then we have things like exponentiation. And I don't know if this should go on this list or not, but we could talk about function composition. I don't think this should go on the list, but I'm going to put it there because it's important to us. So there is an order by which these operations must happen. If you have the number 2 times 3 plus 5, we all learn in kindergarten, and that's an exaggeration, by the way. It's a joke. We all learn in kindergarten that the first thing you have to do is do the multiplication. You don't do the addition first, right? Order of operations say you do the multiplication first. Okay, that's an example of order of operations. Contrast that with if I had 2 times 3 plus 5. Order of operations says you do the grouping first, right? So in this group, you do the summation first. And then you do the multiplication. So I bring that up because of something Alexia asked earlier. You know, when you see this, we need to obey the order of operations. And so when we've got an expression like this, the stuff that happens, right, the multiplication obviously happens there. But to simplify this whole thing, you have to respect the pluses. So that means that the next algebraic thing we have to do is distribute the derivative across all these terms. For example, you can't just factor out an a first, because if you tried to take this and factor it out first, you'd be affecting these terms too. So there's more algebra that implies, right? It's not as simple as just factoring something out. So you got to deal with these pluses first. So now that we have this form, you look at this. The next thing you have to do is you've got to deal with that a. And so we're going to use the constant multiple rule and pull it out. Likewise, here with this b, we're going to pull that out. And then down here at the constant term, we know that the derivative of a constant is 0. So I can take care of that right away. And now I can do the derivative. Now I can take the derivative. I can take the derivative here, and I can take the derivative here. And I'll use the power rule. I guess that's what I mean. Now I can use the power rule. So the derivative of x squared is 2x, and the derivative of x is 1. And so I get 2ax plus b. So that's the derivative of my quadratic. In fact, what I've just shown, and this is what I'm going to say about observe the form that it takes. What I've shown is that every quadratic differentiates to something that looks like this. In particular, this is a polynomial. I'm going to move up here so I'm not down at the total bottom of the space. This is a polynomial of degree 1. So its graph is a line. With slope 2a and intercept b. So this is kind of cool. Every degree 2 polynomial, its derivative is a line, and its slope is twice that coefficient, and it has an intercept that's that coefficient. So I bring this up to you for two reasons. One, it's kind of cool that what the derivative of a quadratic is a line, but the other thing is that I want you to be able to feel comfortable doing a derivative like this where there are no numbers. Math doesn't have to have numbers. Okay. And here we have symbols that stand for numbers. And so notice what's happening here when I go from this second step to this third step. This symbol represents a real number. And so I'll treat it like a constant so that I can use the constant multiple rule and pull it out. So you have to have that mindset that even though it's a symbol, it represents a number, a constant number. So you can treat this as use the constant multiple rule. But notice what happens if you forget. So suppose you forget that's a number and you use the product rule accidentally. So I'm writing this sideways over here. So you'd write this, and I'll come back to this term in a second. And here you get 2ax. And notice that's where you want to end up. But you don't know that yet because you forgot something. But you look at this and you say, what is this? What's the derivative of a? And you remember, oh, a is not a function of x. A is a constant. It's a real number. And the derivative of a constant is 0. And so that logic helps you remember that that's 0. And so 0 times x squared is 0. And then you come up with the right answer. Okay. That is, you end up where you needed to end up, even though you accidentally did the product rule here. It will fix itself as long as you remember that a is a constant. Okay. You do that once or twice, and then you'll remember, oh, my a is a constant, so I can use the constant multiple rule and pull it out, right? That'll save you work.
So the constant rule comes before the multiplication. Will the product rule, is that, and then sum and difference is the first thing you would do?
So if I'm thinking in general, the sum and difference is generally the first thing that you would do.
Mm-hmm.
And then you're differentiating the terms. And then sometimes the terms, you might use a product rule. You might use a quotient rule, depending upon what the term looks like. You have to let the term talk to you and
Okay.
listen to what it says. Okay.
Thank you.
You're welcome.
Oh, really quick, I had asked a question in the chat. Is this the same for the limit laws?
About the order of operations?
Yeah.
Yep.
Okay. Yeah.
Yep. Same for the limit laws. Yep. Good question. All right. So here's another example I want to show you. This example concerns this function 7 over x cubed. And I want to draw your attention to that thing in the denominator. The numerator is a constant, and the denominator is a monomial. And actually, this whole thing is a monomial. But I want to show you two ways to differentiate this. Okay. So here's the first way to differentiate it. It's the obvious way. Let's use the quotient rule, right? It's a quotient after all. So using the quotient rule, we get the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. All right, so let's work that out. The derivative of a constant, that's 0. And so this whole first term zeroes out. And then the derivative of x cubed is 3x squared. So I'll have minus 7 times 3x squared over, looks like I was thinking too sloppy. So downstairs is an x to the 6th. So what do I see? I've got negative 7 times 3, so that's a negative 21. And here, I've got x to some powers. I can use the law of exponents and rewrite this as 1 over x to the 4th. So I get minus 21 over x to the 4th. Okay, so to recap, differentiating this, use the quotient rule, multiplied things out, and then simplified using multiplication and the law of exponents. Here's method 2. So the derivative of 7 over x cubed, I'm going to rewrite that function as 7 times x to the minus 3. And I'm going to use the power rule. Yep. I guess first I'll use the constant multiple rule. Oops. First I'll use the constant multiple rule. And then I'll use the power rule. And notice I'm subtracting 1 from the numerator. And so that makes my, or subtracting 1 from the exponent, I'm sorry. And so that makes my exponent bigger in size because it's negative. And now I can rewrite this in this way. Okay, so notice, same answer, 2 different ways of doing it. Also, here's the Athalia question. Am I done when I get here? Technically, yeah, you could stop right there. There are reasons that this is a nicer way to write the function. One of the reasons is that minus signs kind of screw people up. But either of these 2 ways of writing the final derivative would be equally good. What makes this one better in this case is that we were comparing it to this. And so by writing it that way, we can see immediately that they're the same function. So this method, or this example where I differentiate this in 2 ways, it has wide application. This idea has wide application. And in fact, whenever you have a quotient, you can think of a quotient as a product. And so when you differentiate a quotient, you can change that into differentiating a product. So you'd get f prime times g of x to the minus 1 plus f of x times the derivative of g of x to the minus 1. Okay. But the problem now is we don't know how to differentiate this. Well, don't we just use the power rule, Dr. Miller? No. The power rule only works when the thing you're exponentiating is the variable you're differentiating to. Here, this g is making things much more complicated. This g is intervening and making things change in a weird way. So we don't have the tools yet to differentiate this, but we will on Monday. Okay, I'll show you how to do this. We'll have the tools to do this on Monday.
I don't understand what you mean by the G messes things up.
You will on Monday. Okay, so the takeaway I want you to have for today, right, is that when you see a monomial like this, there's 2 ways you can differentiate it. and that one of the ways just uses the law of exponents. And now I'm giving you a little commercial, a little teaser to this idea that in the future, you can always do quotient rules in terms of chain rules, but the cost is you've got to learn how to differentiate something weird. Okay, so I'll show you how to do this later. So you'll be able to take advantage of this later. All right. 9, 10. Oop. Here's another example we want to work. Find the equation of the line tangent to the graph of f of x equals 1 over x at x equals 1. All right. This is a kind of problem that's going to come up all semester. These tangent lines, we love tangent lines in Calc 1. So I'm going to ask you a variation on this question 1,000 times this semester. So get good at them. So how do you do it? Well, the first thing that you do is you want to determine the point of tangency. Right? And it's going to be an ordered pair. Right? And you want to figure out what's the input and what's the output. What's the x coordinate of the point of tangency and what's the y coordinate of the point of tangency? Well, you'll usually be given the x coordinate or some information that allows you to calculate the x coordinate. In this case, it's given to you directly. It's 1. Then to find the y coordinate, well, it's the y coordinate on the graph of the function f. So we just take our x coordinate and we plug it in for x. Or we plug it in for x here. And so f of 1 is 1 over 1, which is just 1. Okay, so their point of tangency has coordinates 1, 1. So the formula for the tangent line looks like y minus 1 equals m times x minus 1. We haven't calculated what the slope of the tangent line is yet, but we know the slope of a tangent line is the value of the derivative at 1. Okay, so we need to calculate that derivative and evaluate it at 1. Okay. So we're going to calculate the derivative of our f. So f prime of x is the derivative of 1 over x. So I'm going to rewrite this so I can use the power rule because that's easy. And I'm a mathematician. I like easy. So power rule says take your exponent and make it the new coefficient, and then subtract 1 from your exponent. And I do. -1 minus 1 is -2. So my derivative is -1 over x squared. So f prime of 1 is -1 over 1 squared, which is -1. And so the tangent line is y minus 1 equals -1 times x minus 1. And this is a perfectly good way to leave the answer. But if you wanted to, you could go a little further and write it that way. If I ever like grade your work on a learning target quiz, I'm going to be looking for this. And that's probably where you'll see me write a check mark. Okay. Or if you got something wrong, that's where you might see me give you my feedback. Okay. But it's perfectly legit to want to leave your answer like this, though most people would agree that that's fine too. All right, let's do another example. Determine where the graph of the function f of x equals x squared times 1 minus x squared has a horizontal tangent line. Okay, this is a great question. I love asking questions like these. Okay. So what is this question asking? It's asking about a horizontal tangent line. Can somebody in chat or verbally vocalize, tell me what's the slope of a horizontal line?
0.
That was fast, Robert.
My bad. I've been doing this for a while. I'm
Yeah.
kind of like ahead in the book a bit.
Good. So a horizontal line has slope 0. These are our favorite lines, by the way. If somebody asks you, what's your favorite line? You just say horizontal and you'll win, okay? And it's our favorite because the slope is 0, because 0 is our favorite number and one of our favorite numbers in mathematics. I love multiplying by 0, right? I can multiply by 0 pretty fast. So I want to determine where my function has a horizontal tangent line. So I want to know where the slope of the tangent line to the graph of the function is 0. That is, I want to know now where f prime of x equals 0. That's what this problem is asking. Okay. This is how we translate what I wrote in black into how we do a calculation. So the first thing we're going to do is we're going to calculate the derivative. Well, that's the derivative of this. I'm just going to do the product rule because that's the way it's written. So the derivative of the first is 2x times the second plus the first times the derivative of the second. So you can check my work, but you end up with a minus 2x. I'll just repeat that. This is the product rule, because here I've got the product of two functions. The derivative of x squared is 2x, and then these are the same. The derivative of 1 minus x squared is 0 minus 2x, and so I'm just going to write minus 2x there. And then these are the same. So I want to know where my derivative is 0. So I want to solve where does this equal 0. The best polynomials to have when you're trying to solve an equation of a polynomial equals 0 is a polynomial that's in factored form. So I want to get rid of that plus if I can. That is to say, I want to simplify this and then factor it. So let's do that now. So looking at these two terms, is there any common factor I can pull out? Well, I've got a 2x here and I've got a 2x here. So I can pull a 2x out. In the first term, I'm left with a 1 minus x squared. And in the second term, I'm left with that x squared and I'm left with a minus 1. So I'm going to write it that way. I'm going to simplify next. 1 minus x squared minus x squared. So this is 2x times 1 minus 2x squared. So we want to solve 0 equals 2x, 1 minus 2x squared. Everybody with me? Okay. So in mathematics, one of the reasons that 0 is our favorite number is we use this idea. If the product of two things is 0, then either the first thing is 0 or the second thing is 0. So 0 lets us take one equation and turn it into two equations. One equation where your 0 is on the right-hand side turns into two equations where 0 is on the right-hand side. Two simpler equations, by the way. So down here, I've got one equation with 0 on the side, and I'm factored. So I can write this. Therefore, either 0 equals 2x or 0 equals 1 minus 2x squared. The first says x equals 0, right? If you solve this equation for x, you get x equals 0. So that's one place where it looks like our tangent line is going to be 0. The second says, okay, so follow me on this. So this is literally what it says. I just recopied it. Now I want you to think about this one in this way. Because if you think about it in this way, then this expression is the difference of two squares. And maybe I should I'll put a 2 here. Because then we can write it as 1 minus the square root of 2x times 1 plus the square root of 2x. And then we can use this idea again and say either 1 minus the square root of 2x equals 0 or 1 plus the square root of 2x, the 1 plus the square root of 2x equals 0. So x is 1 over the square root of 2 or minus 1 over the square root of 2 if you solve these. Okay. So we've determined x is 0 or it's 1 over root 2 or negative 1 over root 2. I'm going to start writing this on the other page. Right, so those are the 3 places where the tangent line could be horizontal. And we're done. Now, if you're like me, you don't believe it, right? You can believe the math, you believe every step that we did, but you're not sure if it's right. So let me point out a couple things to you. I'm gonna swipe back and show you the previous page. This is a polynomial of degree 4, and the leading term is negative. So it starts out with a negative x to the 4th. Actually, we could write it down. It's negative x to the 4th plus x squared. So its graph goes down like that. And because it's degree 4, it could have 2 wiggles in there. Right? So because the function is degree 4, it could look like that. It could have as many as these 2, I guess 3 wiggles if we count them. That means there could be 3 tangent lines. And in fact, it turns out there could either be 3 tangent lines or 1 tangent line for a degree 4 polynomial that has these properties. So we should feel pretty good that we got 3 numbers here because that's what we would expect from the geometry of a 4th degree polynomial. So that makes me feel better about what we did. What could I do to feel even better? Anybody have any thoughts? What do you mean, Brandon? If you threw in the chat, you said plug it in the chat. What does that mean? zeros, put them into the equation. Ah, so you're saying we've got our function. Did I call it F or did I call it P? I call it F. So we have f of x equals minus x to the fourth plus x squared. We could plug our zeros into here. So we'll plug the first zero in at 0. So that's at 0. And then we could plug in 1 over root 2. And so I think that gives me 1 over 4 plus 1 over 2, which is 1 over 4. And I could plug in 1 over negative root 2, which is going to give me the same thing. All right, so those gave me points that are on my graph, but they don't tell me if this is the place where my tangent lines are horizontal. Yeah, it gave me the points of tangency, at least that my calculations suggest, but it doesn't make me feel any better about, are these the correct points of tangency? Because you could really do this with any numbers, right? I could have plugged in 1, and I could have plugged in -1. I still would have gotten an answer out. I don't know if they'd be the right answers. Anybody else? All right. Nobody? All right, I'm sharing the browser with you. Look what I'm doing. I'm going to draw a picture. I'm going to have a computer draw me a picture. Right? So here's a picture of minus x to the fourth plus x squared. Look at it. That damn thing does wiggle, just like I said it was going to wiggle, right? It goes up, then down, then up, then down again. So does it have 3 points where it's got a horizontal tangent line? You betcha it does. Looks like it's got a tangent line that's horizontal here, a tangent line that's horizontal here, and a tangent line that's horizontal here. So let me go and restrict where I'm plotting this from so I can get a better sense of what the shape is. All right, so that's what the graph looks like close up. So look here. Does it look like it's got a horizontal tangent line at 0? Darn tootin', right? We calculated that it has a horizontal tangent line at 0, and sure enough, the graph looks like it does. What about this right here? There's a horizontal tangent line right there. Well, that looks like it's at about 0.7. Okay. So we calculated the positive x value where we had a horizontal tangent line was 1 over the square root of 2. So anybody want to guess what that is? I don't want to guess. Anybody want to calculate it? What's 1 divided by the square root of 2? Wolfram Alpha says 0.7. Holy crap. Look at that. We got that right. And -1 over square root of 2 is -0.7. So I feel much better about my calculation. Don't you? I think we did it right. I think our answers were right. This function, minus x to the fourth plus x squared, it's got horizontal tangent lines at -1 over root 2, 0, and 1 over root 2. Okay? So this work of plotting the sorry, I just lost my iPad thing. This work of plotting the graph, it's not part of the work that supports your solution. Oh, come on. It's nothing that you have to do to answer this question, right? What you do to answer this question is calculate the derivative, set it equal to 0, and solve, right? And that's what we did over here. Came up with these three numbers, and we were done. Everything else we've done since this point has been to make ourselves feel better. Okay, to check our work. And it takes advantage of what we know about derivatives and tangent lines, etc. Okay, so I will let that go. We've got 20 minutes left. Let me show. Let's move on to another topic here, as defined by the textbook. So this is the textbook's 3.4, rates of change. And so I'm going to spend the next 19 minutes talking about rates of change. Actually, it's going to be kind of a review of what we've talked about concerning rates of change. This is a phrase I've brought up before. It's come up where we've talked about average rate of change. And instantaneous rate of change. So I'm going to assume that you remember what these mean, but I'm also going to help explain, give you a better idea of what these ideas mean in the context of an example. Now that we've talked more about derivatives, you have a better understanding of what derivatives are. But I'm going to start out asking you to recall a story that I told you as we were heading into the topic of derivatives for the first time. Suppose f of x is a function and x equals c is in its domain. And suppose that you know that the limit as x goes to c of f of x equals f of c. What does this tell you about the graph of f? So this tells you something important, tells you something good. And the way I told the story before is it tells you that one of three things could be happening at C in the graph. So I'm going to draw those. So it tells you that the graph of f is continuous at C, right? That's what this means. This is the definition of continuous at a point C. So it tells you the graph is continuous at C. Therefore, one of three things is happening. At the point C, comma f of C, the graph is either going down through it, it's going straight through it, or it's going up through it. That's what this statement tells you. One of these three things is happening, but this doesn't tell you which one is happening. Okay? So what I'm going to tell you now is the derivative illuminates this more clearly. So the derivative tells us, so if you think about the derivative or the tangent line at a point being the local linear approximation to the graph, right? You zoom in. This left picture is when the derivative is negative, right? I should be more specific. The derivative at C is negative. The middle picture is where the derivative at C is 0. And the right picture is where the derivative at C is positive. Tangent line here has negative slope. Tangent here has 0 slope. Tangent here has positive slope. So the derivative is adding new information to this limit statement. And that's pretty cool. Okay, that's really kind of cool. And so what we're going to start talking about is what can we do with this new information? What good does this do us? And it does a lot of good. It is really pretty cool. So for the rest of the class, for the rest of the time, I want to work with a special function. We want to consider what's called the position function. So say S equals S of t, okay? Where S of t is the position of an object on a number line, like the real number line, at time t, time t. So we've got a number line, it's got 0, positive numbers, negative numbers, okay, and we've got some object on it somewhere. So I want to do more. I'm going to say t is time measured in seconds, and s is a distance. Well, let's not say distance. Let's say position. And we're going to measure it in meters. So on my number line, you can think of it as like a tape measure that's pulled straight out. So we've got something that's moving along the number line, and its position is measured in meters along that line at various times t. So if I were to graph my function s, right, I'd have a time axis, and I would have a distance axis. The distance would be measured in meters. The time would be measured in seconds. And yeah, I'd have measurements on the axes. And my graph of S of t would look like this, right? So this is a t-axis. This is my s-axis. Okay. And so S of t is called a position function. Also known as a displacement function. Okay, so this is the scenario. I've got a function. Input is time, output is a distance measured in meters, time is measured in seconds. So let's pick some time. I'm going to call it t sub 0, and we'll assume it's positive, assume it's sort of at some future time. And sometimes you think of negative numbers being in the past. And so let's consider the derivative of my position function. So S prime of t naught. So I'm going to write this in two ways. So here's the derivative definition, the limit definition of the derivative. And I can rewrite this using delta notation. So H in that first line is really delta t. It's how we're changing the input. And here I'm just making that more explicit, delta t. So this is the derivative. So what I want to remind you is that we had talked about this thing here as a quantity delta S over delta T. Change in S over change in T, right? That's like the slope of the secant line. Okay, on the graph of my function. Rise over run, change in S, right? Change in S divided by change in T, so it's a slope. Okay. This is also called, in general cases, the average rate of change of the function. And we've talked about this before. And in this particular instance, for a position function, it's called the average velocity of my object. Why is it called average velocity? Well, look at the units. Delta S and delta T. The unit on delta S is meter. The unit on T is second. So the unit on the whole thing here is meter per second, which is a unit of velocity. So in the case of a position function, when we look at these delta S's over delta T's, we get a measurement of velocity. Okay. Which is very important. Then when I take the limit, what's happening? Well, the average here is an average velocity expressed over an interval, right? It's over an interval of time, delta T. And so over this interval of time, delta T, my object starts at one position and it ends at another position. And this difference up here is the distance it traveled, the total distance it traveled over the time it spent traveling that distance. And so that's why we call this an average velocity. But as we let delta T go to 0, right, in this limit, that time interval disappears, it vanishes, right? Delta T is going to 0. So that thing we're calculating an average over, it's vanishing. And so we get what we call I'll do this in blue, an instantaneous velocity. Okay. And so that's what S prime of T is. That's what ds dt is. Okay, an instantaneous velocity. So that leads us to say something like this, and I'm going to swipe to the next page. I've got 8 minutes left. Thus we say, if S is a position function, then S prime is a velocity function. Right? Velocity of the object at time t. Okay. Oftentimes we'll write v of t for velocity. So v of t of my velocity function is the derivative of my position function. So this is pretty cool. It's a real life application of differentiation. If you know the position of something at many points in time, you can estimate its velocity. Well, for everybody who's got a driver's license, that's kind of obvious, or everybody who knows how to ride a bike, that's kind of obvious that you can do that. Or if you're a jogger and you've got a GPS unit on your sport watch, you can do that. But even if it's obvious, here it is mathematically. Here's how we do it. The velocity is the derivative of position. Let me say more. Dig deeper in on this. So the derivative, okay, which is velocity, is approximately equal to the average velocity when delta t is small. Okay. So for all intents and purposes, assume delta t is always positive. That time is marching forward. Okay. So that's always positive. So what does that mean? What does that tell us about the numerator? Okay. Delta S is the new position, like the new location on the number line, minus the old position on the number line. That looked like cold. Okay. So if delta S is positive, then the object moves right. So I just drew a number line at the top right of my iPad screen. If delta S is positive, then the new position is bigger than the old position. That means the new position is to the right of the old position. That means the object is moving to the right. Okay. So if delta S is positive, that means, delta S over delta T is positive. That means ds dt is positive. So when the object's moving right, the derivative is positive. The same logic tells us if object moves left, the derivative is negative. Because if delta S is negative, then the new position must be smaller than the old position, right? The new position must be smaller than the old position for those differences to be negative. So that means the object is moving to the left. And then the last possible case, right? We've got a positive derivative, we've got a negative derivative. The case where ds dt equals 0 means that the object is stopped for an instant. Okay, that's the instantaneous rate of change, is when the derivative is 0. And what I like to think about to help me understand this case is, has anybody ever been on a swing, like a playground swing? As a little kid, not like yesterday, not like this week.
Yeah, I have.
So if you've been on a playground swing, you know, when you swing back and forth, when you're swinging, when you're at the front height of your swing, it always feels like you stop for a second. And that's what's happening. You are stopping for an instant. Okay? And it turns out you're stopping because you're turning around. You have to go from moving left to moving right. And that requires a stop for a second, because think about your derivative has to go from negative to positive. And so it's got to pass through that 0 by the intermediate value theorem. Okay. So when your derivative is 0, you're stopping even just for an instant. And sometimes that just means you're changing directions. So in the context of position functions, the derivative has a really important interpretation as an instantaneous rate of change. It lets you talk about the velocity of an object if you know its position, and then it lets you determine when the object is moving forward or when it's moving backward, right? On a number line, if it's moving up the number line or down the number line. And that's really cool. In the last 45 seconds I have, let me go back to this picture that I drew at the beginning. When we're talking about differentiations as rates of change, we'll do this in terms of x's. So I've got y equals f of x. What I'm interested in learning through the derivative is, as I change my input, as I change my x, how is y changing? As delta x, or as x changes, how does y change? Right, and this leads us to statements like rate of change of y with respect to x. So you'll see me write this a lot. You'll see the book use this phrase a lot. This is a phrase that's central to the calculus. As x changes, that's what this with respect to x means. As x changes, what is y doing? In this case, as I move x up, y goes up. As I move x down, y goes down. So the function tells me y is doing the same thing that x is doing. If I had my graph with a negative slope, y would do the opposite thing that x does. And how fast it does it is all about the slope. So this phrase is really important, rate of change of y with respect to x. And that's why this stuff down in the bottom is important in Leibniz notation, because this tells you what's happening here, okay? This is the with respect to x, and that's why that's important. All right, I'll stop there. I went over time a little bit. I apologize for that. Thanks everybody for hanging in there. We lost some people along the way. Hopefully they'll come back and catch it on the video. Anybody have any questions before we call it a day? Mason, you got your hand up?
Yeah, I had a question about the quizzes.
Yeah.
So I have to print it out at Staples, and I noticed you said like we have like 20 to 30 minutes once we like open the file. If I have to print it at Staples, could I bring it home, turn it in? It might take me a couple more minutes to bring it home, if that makes sense.
Yeah. So in the best of all possible situations, right? If you could print it out at home and take it, then I think it's going to take you 20 to 30 minutes. But don't ever stress out about how long it's going to take you. If you have to do the Staples thing and it takes you 45 minutes from download to finishing, and you feel nervous about it, just send me a note. Okay. I'm not going to worry about it. It's if I look and it's taken somebody 2 hours, that's when I might send them an email to ask them what's going on, but don't stress about it. And then also, Mason, you're also free to look at the Learning Target quiz on your computer screen and write your answers on another piece of paper.
Okay, so we can do that?
You can do that. The problem with that is that there's some geometric stuff that we're doing that makes it kind of hard to do. But some people don't have printers, and so I commend you for making the Staples run every time you want to take a quiz. But I just want to let you know that you don't have to do that. Okay.
All right, cool. Thank you.
You bet. Thanks for the question. Yeah, what's on your mind, Jet? I can't hear you. You're not muted, but I can't hear you. I still can't hear you. Hey, Jet, why don't you give me a phone call? We can talk that way. I'll put my cell phone number in the chat. You can call that. Okay. Anybody else got anything? Oh, I hear something. Okay. Yeah, Robert.
Okay. So I was going to say, next week, will we go over higher order derivatives? Because those were in the book, but I didn't really understand the process.
Yeah, I'll talk about those too. I'll put them on my list for next week.
All right. That's all I was wondering. Thank you.
Okay, cool. All right. Well, I'm going to call it a day unless Jet figures out how she dropped off. Okay. All right.
I have a question too.
Sure. Yeah, go ahead.
So what are your times that I can meet up for office hours, and what's the Zoom link again? And how can I get to you?
All right. So I'm going to share a web browser here with you.
All right.
If I can find it. Okay, got that. All right. So you should be seeing a web browser now. I'm going to do the CI thing. Log in. I'm going to go to Canvas.
All right.
I'm going to go to our Canvas site here. I think Jet was just trying to call me. So here, clicking on our Canvas site. So I'm gonna.
Oh yeah, I see it right there.
Yeah. So right here. So this is the landing page, and this is the way you should see it. So here's the Zoom meetings for us in section 1, and then this is the office hours.
Okay.
So anytime you want to meet with me one-on-one, this is the link that I'm going to use.
Okay.
Yeah. Does that answer your question then?
It does.
And then student hours are right here, but you can always make an appointment to talk with me too. Okay.
Okay.
All right. Is that good, Evan?
Yeah, that's good. Oh, but also, I was planning on going to Lupe's drop-in hour tonight. Is that fine? Where do I go to do that?
All right. Let me share this with you again. So we're going to go back to the Canvas page. So down here at the bottom of that same page, it's got Lupe's drop-in hours for class. And then here's the link for connecting with him.
Oh, okay.
Right? Is that right,
Yeah.
Lupe?
Yes, it's a page on the CI website. You go ahead and there's gonna be like a blue button. It says request a tutor.
So right here, request an online tutor.
Okay.
That will
So-
take you to.
Yep.
So I just go to that when it's like 7:30 because that's when the drop-in
Yep.
time is. Okay.
And then Lupe said he's there until 9:30 tonight, but it's 7:30 to 8:30 that you get to jump the line.
Okay.
I'm there till 9.
9 o'clock. 9 o'clock. I'm sorry. All right. You good, Odell? Dunya? I guess so. Okay, good. You good, Lupe? All right. And then we'll meet tomorrow. Yeah. Okay.
Okay.
All right. See you, everybody.
Thank you.
You bet.